Okay, now it's my great pleasure to welcome another colleague, and that's Professor Nitin Nitin. He's going to talk about functional packaging to maintain produce quality and safety. And Professor Nitin is from the Department of Biological and Agricultural Engineering here at UC Davis. And his interdisciplinary approach encompasses biomolecular engineering, mathematical modeling, material science, and molecular imaging. When working on food engineering research, his goal is to develop technologies that address key food safety issues. In 2013, he received the Samuel Kate Prescott Award for demonstrating an outstanding ability in food science and technology research, and was named a UC Davis Diane M. Barrett Fruit and Vegetable Faculty Fellow in 2016. Welcome, and we look forward to your presentation.
No, thank you, Beth, for the kind introduction, and thanks for the opportunity to Arvind and Beth. This is an excellent opportunity to share some of the work that we've been doing, but also, just like my colleague mentioned, it's an opportunity for us to learn, because some of the topics that I'm going to present, we do work closely in those areas, but maybe sometimes from a different angle. So I'll share my experience as we move along. So one of the goals of functional packaging, as Beth and my colleague Gang mentioned, that we're often looking at improving the barrier properties. And these barrier properties may be related to reducing the ethylene production, controlling the water vapor transmission, oxygen transmission, UV light. In some cases, we're looking for these functional packaging to improve antimicrobial and antioxidant properties, which may also be related to delayed browning in product, as well as preventing the loss of color, resulting in the loss in quality. So these are some of the examples of how we use functional packaging or functional packaging solutions as. And often these are overlapping interests. So it's possible that one of the materials may provide both reduced ethylene production and may also provide barrier against fungal spoilage. So you may have two functions or more than one function in a material in many of these cases. So a concept that I'm going to share today is related to edible materials as coatings, building on what Professor Gangsung introduced. These are the biomaterials that are derived from natural sources, and they are used as packaging materials in this case. And one example is that these materials are directly coated on the surface of a produce. And then what we're looking for in these materials is their ability to control the flux of oxygen, carbon dioxide, and water. In some cases, we are also looking at their ability to control the ethylene levels that are being produced by the produce itself, as well as controlling the antimicrobial activity. So we're looking for multiple functions in a single coating that we may be able to coat on a produced surface. And since you may be thinking about how this gets coated in an industrial setting, there are many ways this can be coated. One of the simplest ways is dip coating that has been used in the industry, where the material may go through a dipping process and a drying process, which result in a coating. The other application that I have seen in industry is the spray coating, which is widely used in many of the fresh produce industry, where they may use wax as a spray or even other edible polymer as a spray. And these spray coatings can result in a coated polymer. In small scale settings, they can be also brush coated, although that is less scalable as you think about the scale of the application. The spray coating is generally one of the most scalable process, where you can have a conveyor belt. As the material goes through, these coatings can be deposited on a produce and may result in functional improvement of the product. I want to put a plug in for UC Davis, since I'm presenting on this field and I have my colleagues here. UC Davis has been a pioneer in this field. We often don't get branded as a packaging school when you think about packaging, but UC Davis has been a pioneer in many areas, including edible coatings. And I'm sharing a picture of our former colleague, Professor John Proctor, who is retired. And Professor John Proctor led this field for many years. and has contributed with over 180 publications and many books and other things. So I just want to highlight some of the work that he has done in this area. Even before this area became a key interest in the produce community. For example, like all of you are familiar with companies like Appeal, which are trying to commercialize edible coatings to preserve the shelf life of produce. This area was well researched and well developed at UC Davis, 20, 30 years before that. So it takes time sometimes for technologies to move from the university space to the commercial space because of many factors, including the money. So this is just one example of it, where it has taken some time for it to evolve in that direction. So I'll share some results from the literature where people have shown some of these properties of edible materials to improve the barrier properties as well as slowing down the respiration of it. So I'll start with that example as a first case scenario. So this is an example that comes from a study that was conducted using silk, which is silk fibers as edible coating to reduce mass loss. The study focused on strawberries. As we all know, strawberries have a relatively very short shelf life. And they focused on strawberries to understand if the coating of the silk fibrons can reduce the loss of mass during storage. And what they showed was that without the coating, they lost about 70% of the mass in about 12 to 14 days. And using the silk fibers as a coating material, depending on the data sheet content, they were able to reduce the loss by at least more than 50% of it. So it just illustrates the application that using a biopolymer that is derived from insect in this case, we are able to provide a protective coating in terms of reducing the mass on the produced surface itself. And I like this study because it's very demonstrative in terms of the quality of the sample that has gone through it and illustrates very clearly the application there. Now, since we talked about some of the properties that we look for when we make an edible coating, so some of the things that we look for are their ability to conduct water, the hydrodynamic permeability. We look for their ability to prevent the diffusion of water in the film, because water migration is a big problem in the produced quality. So if you can preserve the water, you may be able to maintain the freshness and potentially the quality of the produce. As well as the oxygen diffusion, we talked about earlier that limiting the diffusion of oxygen from the environment into the produce could be one way of preventing that spoilage from occurring. And this may go potentially hand in hand with MAP coating or MAP environment, where you may be able to provide with consumers a product that combines edible coating and a MAP environment. So where the edible coating allows you to maintain the MAP environment once you take the package home. So there are opportunities of building that synergy between building the MAP modified atmospheric packaging environment and some of these coatings in this case. It was remarkable what they showed in terms of the firmness of the coating. As you can see that without the coating, they lost significant value of the freshness or the firmness of the fruit. And with coating, they were able to retain most of it even past a week or so of storage. So these are some of the features that we look for when we think about the functional product and its interaction with the produce in this case. And remarkably, they also showed that using high beta sheet content in silk, in this case, they were able to depress the respiration rate. So the strawberry respiration rate significantly reduced as the beta content of the protein increased, the beta sheet content of the protein increased. And again, you can compare that to the without coating, which is significantly larger. So it's about 3 to 4-fold slower respiration rate over a period of time. Now, when you make a coating, it's desirable that the same solution can be implemented in many other products. It's not only about strawberries, it's also about other produce also. So one of the things that this study showed was that this can work on multiple varieties of fresh produce that could benefit from edible coating research. For example, in this case, they are illustrating the quality of the bananas that is preserved by using a coating process. Again, bananas are highly respiring produce and produce significant amount of ethylene also as they ripen. So ability to control the respiration rate as well as maintaining the loss of water preventing the loss of water, they are able to maintain the turgor and the mechanical properties of the banana, giving it a freshness over extended period of time. So I will take another case study looking at the functional properties. In this case, I'll focus on the antimicrobial properties, and I'll try to cover antimicrobial properties from, again, edible coating perspective, and we'll be looking at both UV barrier properties as well as the antimicrobial properties of the produce. So some time ago, my lab was interested in understanding how can we use biocontrol strategies to prevent both spoilage and pathogens, foodborne pathogens which cause disease in this case. One class of material we were exploring was bacteriophages. For those who don't know bacteriophages are the viruses that are very specific for target bacteria. They can be applied in the produce setting, in the pre-harvest system, as well as they could be applied in the post-harvest. And the objective here is that they will prevent the spoilage bacteria or the pathogen, depending on the phase that is designed for, to be useful in extending the safety as well as the quality of the produce. Now, one of the challenges that came up with is that, like many other agents, these viruses are very susceptible to light as well as desiccation. So if you put on a produce and it goes through a desiccation cycle, you lose significant activity of this agent in this case. So our objective was that how can we use the concept of edible coating in this case to maintain the activity of the biocontrol agent. So in this case, the edible coating is not only providing protective barrier against the loss of water, but also, or respiration, but also actually protecting the active biocontrol agent that you have in the formulation. So we had done some study before that where we had looked at how edible coatings could improve the stability of biocontrol agents during storage. And as you can see, without the coating, you lose significant amount of activity. And this is on a log scale. So you're losing activity not by linear scale, you're actually losing activity on a log scale. So by losing 5 log mean that you have lost 10 to the power 5-fold activity of your agent in this case. By using some of these edible coatings, we were able to stabilize these phages on different surfaces, including plastics, and they could work in ambient and storage conditions. And the same concept could be extended to other microbes which are susceptible to decay, but may have a biocontrol perspective on them. We designed some polymer particles which are designed with using food grade materials, dopamine. So these are polydopamine particles which were designed to maintain the UV protection properties. So we added those to the film. And as you can see, even without see if I can use a pointer here. So even a very short period of UV exposure can result in about 2 log inactivation of these phages. And we looked at if we add small amount of polydopamine particles, we can preserve the activity of this biocontrol agent for an extended period of time against UV protection in this case. Again, this is the case if you were to spray it on a product and being exposed to light, you would lose significant activity without this protective coating as illustrated here. And one of the next tasks for us was to see if it would work on a produce surface and we can expose the produce to that environment and test it. On a produce surface, the loss is even more acute. So for example, you could lose about 3 to 4 log if you just spray this agent on a produce surface. And that's a big barrier in using some of these biocontrol strategies for foliar applications. When you try to spray on a plant and you cannot protect the biocontrol agent from desiccation loss or UV induced damage. And some of these coatings could provide some of those barriers in this case. We also demonstrated in this study that these agents do not interfere with the activity of this material, and we can maintain the activity, which is the biological inactivation of the bacteria, and significant inactivation as compared to the controls, where you only get 1 log inactivation. We can get 3 to 4 log inactivation by protecting the agent and maintaining its shelf life for a longer period of time. And it also works in terms of protection, not only in terms of challenge assay, we could also do protection assays where we could show that if the bacteria were present before and you combine this with the agent, they would protect against it. So they would take the challenge and maintain the activity. Again, the theme here is to highlight that the edible coating materials with certain functionality against UVA control could extend the use of biocontrol strategies in fresh produce. And they can protect them from against desiccation as well as light stresses that may be present in pre-harvest or post-harvest environments. So the next topic that I want to talk about in terms of functionality, so far we have talked about materials that are present and they do not change with time. But there are a lot of functional materials where we want controlled release of materials, and these are typically volatiles and gases that we are interested in controlling release of. Some of them we want to use controlled release to reduce the ethylene production. Some of them we want to use for antimicrobial properties. In some cases, we want to use these volatiles and gases for delaying the browning processes in the produce itself. And there are many examples of it where we use different setups to do this process. For example, in one case, you could have a gas generator that would interact with the pellet of fruits to distribute this active agent. You could have a packaging material where this is coated on the surface, and this material would be released over a period of time to maintain the activity in the packaged environment. Or what has become very common in the industry is these gas generating pads, where they have these functional pads that could be provided as a material that could be used to control the distribution of the gaseous or volatiles in this case. And the dots indicate here the active compound that's being released. I'll talk about the examples of some of the active compounds that industry is interested in. So one of the compound that the industry is interested in is 1-MCP. It's one of the potent inhibitor of ethylene. It's a ethylene scavenger and suppresses the ethylene activity in produce, help extend the shelf life of the produce. So based on the literature, there are many products out there, different companies with different trade names. And this field actually really changed significantly because the patent on 1-MCP use actually expired in 2018, and a lot of companies could get into this market and actually start making products with their different formulations. If you look at it, most of these formulations are using alpha cyclodextrin, which is a molecular trapper. If you want to think about it, it traps the MCP in a trap, and based on the humidity of the environment, it releases this 1-MCP there. The other that has emerged is the metal organic framework. These are very good absorbers of gases, very sensitive to humidity, and can provide controlled release over an extended period of time for post-harvest applications. Then something that has emerged also recently is the activated carbon, where the activated carbon is used to absorb a 1-MCP, and this sachet of activated carbon, which is more benign than metal organic framework, could be used as a material to provide the release in this environment. So in the interest of this session, I just want to briefly talk about the encapsulation systems that are typically out there. So, the typical encapsulation system that are used could be liposomes, cyclodextrins, emulsions, microparticles with shells. And they all the motivation comes from different type of biological structures that exist in nature. Um, the mammalian cells, the milk fat globules, or the plant or microbial cell. In our research program, we have been interested for some time to develop encapsulation system for controlled release. One of the applications we have been working on is to use yeast as a carrier material for controlled release applications. And I'll illustrate some of the applications of it. So we designed a process which allows us to partition compounds into yeast cells. And we can concentrate high concentration of active ingredients, volatiles, non-volatiles in this environment. And again, the partitioning is designed based on the principles of thermodynamics, which allows the compound to select the specific strains of yeast and partition into it. And we can control the kinetics of the process as well as the release in this case. One of the applications that we are working in this area is to improve the stability of essential oils and some of the other ingredients over an extended period of time. And these essential oils are one of the categories of volatiles that have been of significant interest to the produce industry in terms of both antimicrobial properties as well as some of the ethylene suppression properties of some of the essential oils. So we can get very high yield. We can develop stable formulations which are stable for extended period of time. When exposed to moisture, we can design their release profiles. We can design fast releasing, slow releasing materials from different compositions of the yeast itself without changing significantly. These are some of the images of the yeast cells with the encapsulated essential oil in them in this case. And not only that, the agents that we select can have affinity for your target microbes. So if you're interested in, let's say, inactivating bacteria and fungi, we can select yeast strains with specific affinity for them so they can bind them more effectively. These materials can be used as a filler, like as an insert, package insert, or they could be used as an edible coating because they're perfectly edible in this case. They're made with yeast which are inactivated. So there's no barrier in their application, and they have good binding affinity against different pathogens of interest. Here I'm showing an example of it where this material shows significant inactivation of Listeria biofilms on model plastic surfaces in this case. And what was very intriguing to us was the residual effect, that even if we just co-incubate this in the vicinity of it, it prevents the formation of biofilm. And its effect is quite persistent. Like if you use free thiamol, it does inactivation early on, but after 24 hours, the Listeria start growing back. But with this agent, you are able to maintain the persistent concentration in that area for a longer period of time. So even after 24 hours, you have significant inactivation of the material in this case. And if you co-incubate with biofilm, definitely it provides a better inactivation than free thiamol, because free thiamol is very volatile. It evaporates very quickly when you incubate with the biofilms in this case. We are doing some ongoing studies to understand how we can control some fungal spoilage issues as well as ethylene suppression or scavenging. We are thinking of integrating some of these edible coatings on product and packages, and we'll look forward to your advice and recommendation from the audiences here as well as online to see if there are particular interest applications that may align with it. So coming to my last slide, I'll talk about, hopefully I've shared with you some of the developments in this area of edible coatings and their functional role in functional packaging, either as a barrier properties, antimicrobial properties, or improving the quality and extending the shelf life of the product. Thank you very much. I'll be glad to take any questions.
Have you ever tested this commercially available solutions like Appeal and others? And what is your comment regarding this?
So I think that's the solutions. I've not personally tested them in the lab per se, so we have not had a chance to test any of their materials per se. But from what I know, some of the studies that we have done and probably more others have done, what we find is definitely using some of the edible materials, you can suppress the water loss from the produce, and that could lead to extending the shelf life significantly. You can also suppress the oxygen permeation properties, and that makes a big difference in terms of extending the shelf life there. So as I understand, the product that Appeal offers is actually one of the things that material provide is the barrier against water loss, which is one of the biggest variable that they control. The other variable is the oxygen barrier properties in this case. There are some other materials that are being developed, and I'm actually glad that companies like Appeal and some of the other with Zane-based coatings like Flozane and others have come up, because this field has worked on for last, as I said, Professor John Proctor was working in 1989. So And just because of the cost and some of the logistical issues and the availability of the raw material, this field was not moving forward. So with the success of, at least the initial success of some of these companies, I'm actually very pleased to see that the field has a new direction and the potential to develop more effective solutions that may integrate other functionalities. So I think there's definitely a potential for those. Improving the barrier property makes a big difference in the shelf life of the product.
Thank you. Great presentation. When you suggest to apply the coating, or when you can have the best effectiveness, right away after the harvest or weeks later? Because in certain commodities like apples, pears, avocados, we don't pack right away, you know?
Sure.
So is there any different from that? After harvest and or before? Right?
So I would say that to the best of my knowledge, I'm not aware of that studies that have looked into whether it is the initial period or the later period, if there are differences in those activities. But I would imagine that if you want to integrate with your, it's much easier to apply these coatings during your packaging operations, just because you clean the produce in many cases, and then you're able to apply the coatings as during the drying process or other steps in it. It's much easier to apply coatings in that stage than during the harvesting stage immediately after. Unless you have operations at the harvesting point where you have nozzles and other things that you can apply these coatings on the product itself. So I would imagine that from the logistical perspective, it's much easier to apply. Whether that is optimal or not, I'm not sure if I have the answer to that question. If it would be much better to apply it like at the time of harvest, just to control it itself.
Yeah, no, basically, for example, after the food is cut, but sometimes we keep apples and there's in storage
For even more than 2 months. Yeah.
Can I apply the coating up 2 months after the harvest?
Yeah, I think you can still apply it, because when you do the problem is that when you store the product, you are storing under cold temperature. Yeah, you have a modified atmospheric conditions in many cases in your storage conditions. You may have small amount of ozone and other things to preserve the microbial growth. So you're doing all the active management of the processes. So you are doing some things that are extending the shelf life during storage. So these coatings can help in terms of even after you are harvested and you have stored and at the stage of packaging, they can still be useful, because that's when the product goes through most variation in temperature, most variation in humidity, and other external factors that are sometimes beyond your control. And also, I think, as I mentioned that, there may be an opportunity, what Beth mentioned, that, how do we get MAP extended to consumer products? Where some of these coatings may provide extended barrier even as they go to the consumer, because they are part of the product. They are on the surface of the product in many cases. Some of them could be doesn't need to be on the surface of the product. I think with one MCP control release formulation, we are seeing that they can be just an insert in the package in some cases. So I think there's a lot of potential for some of these materials to be part of the package or the part of the product, and can be applied in many stages of it. Yeah.
I've had some cases with apple packing, there was a two-step process, like pre-sort and the storage last supply, and then stored for a long period of time, and then I unpack with the finish. That's not the same process you're describing. Okay. No, thank you. So basically, it was my doubt was about the effectiveness of the coating appeal Harvista. That's pretty good too. Right away and after the harvest, at the packing, or a month later in fruit that was exposed or stored under CA condition, apples, pear, or kiwi, so effectiveness.
I have a question about the yeast-bound E. coli. If a human consumes a bunch of yeast-bound E. coli, does that present any problems to them? And then also does the yeast-bound, does that create any byproducts?
Sure.
The yeast create any byproducts?
Sure.
By that binding?
Yeah, thank you. Thank you for the question. So this is an interesting question. So if a slice of bread has about 1 gram of yeast. So, when you get a bread, so we eat significant amount of baker's yeast all the time. So the amount of yeast that we use in this application is in milligram range. So it's much, much less than what a bread would provide. And these are inactivated yeast. So they're not live, they cannot grow. They are just as a carrier there. And we're using their cell surface to have affinity to bind other microbes or other things so that they can deliver better functionality of the antimicrobial or the other agents. And we're using their affinity also to bind plants itself. We are using their affinity to bind plants itself so that they stay on the surface for a much longer period of time naturally. Yeah. Or the plants. Yeah. So we are using their affinities, natural affinities that they have. Some of them are weak affinities, some of them are strong affinities. But you can design that based on the strain combination you choose. But baker's yeast itself has very broad affinities. For example, we were surprised that this baker's yeast strain actually binds Listeria, E. coli, and Candida very well. Yeah. So it will actually kill the yeast in this case. It will kill the E. coli if there was any E. coli in there. Yeah. So it will not concentrate from the environment. It will only take care of what is on the produce itself to start with.